No?
Okay, let's start our session. Maxim Kontsevich will give their talk on the subject, which doesn't of the family. Related to the subject of this.
That's not related to subject of this conference. Yeah. Yeah, I hope you'll just kind of like entertaining talk. Yeah, yeah. So it's not A, not B, it's something else. I don't know. C, maybe C. Yeah. Yeah. So it's really very classical elementary topology, and as I said, that has nothing to do yet with symplectic topology, and it has little to do with algebras, non-commutative algebras, which you like. But homological algebra is very rudimentary. It's zeros Hochschild homology. It's a quotient of the ring by commutant. And it's even more primitive than general Hochschild homology because, like we heard yesterday from Simon Dreshchikov talk, for Hochschild homology, you need base ring, commutative ring. Here we don't, for zero homology, you don't even need base commutative ring. This quotient is dependent. It's over Z, over C, whatever. It's the same quotient, yeah. So the zero Hochschild homology is very, very basic thing. And I will apply it to what? To the ring, which is group ring of a finitely presented group, fundamental group of some finite cell complex. Yeah, finite cell complex, and it's connected. Yeah, this ring, it's not the ring which we like. Yeah, we prefer it's at least in symplectic topology. There's a better ring. It's your DG ring. You consider chains with integer coefficients of the topological monoid of base 2 loops. This is much better ring, but it's zero. It's concentrating non-positive degrees, 0, -1, -2, homological degree. But homological degree 0, it's usual group ring of the fundamental group. You forget about high homological groups. And why is this? Think it's kind of better because it's homologically smooth and kind of finitely presented, or finite type in sense of turn Wiki. So it's something like smooth variety of integers of finite type. So not compact, but smooth and really nice object. And in symplectic topology, it also has some meaning. Namely, you consider cotangent bundle to some manifold with boundary. Consider cotangent fiber at any point, and consider endomorphism wrap for high category, and also wrap in period boundary. So you get this exactly this guy. Yeah, it's a more scientific point of view, but for the zero Hochschild homology, it doesn't change anything. Because if you just move things to the left, you still get the same more quotient by commutants. So it's all advanced science, it's completely irrelevant for my talk here. Yeah, so now I'll tell you the story, which is this year will be exactly 100 years old. In 1926, Jakob Nielsen discovered his basics of his fixed point theory that he developed in several years. So we have the question is the following. You get some topological space, usually he was thinking about compact, and get a map of this guy to itself. And you want to have some low bound by pure reason of number of fixed points of this map. And he discovered that if the space is, let's say, polyhedron or finite cell complex, and if it has non-trivial fundamental group, then you get a remarkable low bound. If it's trivial fundamental group, I'll tell you what's a low bound. You will see in a minute. It's very stupid. Yeah, but for non-trivial, it's actually maybe I tell it. If the answer, if fundamental group is trivial, then the low bound will be 0 or 1, depending on Taylor characteristic of you guys. Non-zero or 0 or 0, yeah. That's it. Yeah, so so it's, but for non-simply connected cases, it's something very big number. Yeah, first of all, we can define mapping torus. You multiply your space with a polyhedral space by interval and glue endpoints according to the map. If it will be automorphism of space, then I get actual vibration, but it's general for singular guy. And obviously, each fixed point gives a closed loops in the mapping torus. And these closed loops have degree 1 if you map this mapping torus to the circle. So that's the picture. We get not invertible map, say. You get some fixed points at the right point. You follow this trajectory, you get closed loop. And the projection I told you is vibration if the map is invertible, vibration in topological sense, local trivial vibration. And if it's not invertible, it's not vibration, but it can still be vibration in the sense of SER if it's homotopy self-equivalence. But if it's not homotopy self-equivalence, it's not in vibration in SER sense. And homotopy type of this mapping torus depends only on morphism in homotopy category of spaces. And so there are, like these days, we can denote these things in different way. Like homotopy co-equalizer of pair of maps, identity map and this map phi. Or homotopy co-limit of this diagram with two vertices, two arrows. So it's some scientific way to see it. So you get this mapping torus. And if it's finite, finite cell complex, then it will be mapping torus will also finite cell complex. It's very easy to see. Okay, so each fixed point defines a homotopy type of a free loop in the mapping torus. Element of place of free loops, by zero place of free loop. In fact, when Nielsen developed the theory, he used a different terminology. He introduced the notion of twisted conjugacy classes. And it's a bit more precise description of what we have. We get twisted, it's not exactly the same thing. I'll explain the difference. Okay. You get twisted conjugacy class, and we can certainly assume that this my cell complex is connected and choose one of fixed points, and it will be for me like base point to speak about fundamental group, because I cannot, without base point, I cannot speak about fundamental group. It should be groupoid. So this map phi use some endomorphism of the fundamental group. And the notion of twisted conjugation, it's in general for group and endomorphism, not necessarily invertible map. And two elements are called twisted conjugate. If there exists a third element H, you get conjugation, but first H you apply this endomorphism psi, and it's just, you can immediately check that you get equivalence relations. It's reflexive, symmetric, and transitive. So you get some notion of twisted conjugacy classes, and how to do it geometrically. How to get for any fixed point or any other fixed point twisted conjugacy class. So you get x0 is one of my fixed points, which I treat as a base point for speaking about fundamental group. Now I choose another fixed point y. Because space is connected, I can connect by some path to y, x0 to y. Then apply automorphism, I get the same path. Actually, should be phi inverse. I get another path from x0 to y as well. But now change orientation, compose them, I get a loop, get element of the fundamental group. And if I can draw a little diagram, if we make two different choices of passes, then it will be twisted conjugate. And now there's a lemma. yeah, so we have two languages. You get twisted conjugacy classes and also usual conjugacy classes, so the fundamental group of a map torus. The lemma is that the map from set of twisted conjugacy classes to set of ordinary conjugacy classes of degree round with respect to this map to circle is an injection. So you don't lose information if you speak about this ordinary conjugate classes of the fundamental torus. Yeah. It is a very easy classical factor invertible automorphisms. That's very tautology. But for non-invertible automorphism, it's 48 hours old result. I just proved talking with ChatGPT, waiting in San Francisco to apply it here. It's really not trivial. Yeah, it's some kind of nice new result, nice reformulation of classical theory, which people miss for many, many decades. Sure?
Not ChatGPT.
Not Chip, no. The main contribution was by me, not. Second of the possible. Okay, yeah, but yeah, you get actually we proved some even more strong result, but okay. I don't know what those details. Yeah, for each twisted conjugacy class, you can Nielsen said that have associated invariant independent of what exactly the map you have, depends on the homotopy class of the map, and it will be some integer index of this twisted conjugacy class. How to define it? If you have polytope, you can embed to Euclidean space, take some name, replace by manifold. Manifold with boundary, compact manifold with boundary. And choose a generic smooth representative of the map, just smooth map from a manifold with boundary itself. And because you can shrink the boundary, you can assume it's not really non-invertible, you go to strict interior by this map. So you, like in my original picture, you go to strict interior, you don't, there's no fixed points on the boundary at all. Yeah, so it makes interior, and we can assume that this guy is generic. Then I get finitely many fixed points because it's compact. You get the transversal, and the intersection of the graph with diagonal will be transversal. And then for each intersection fixed point, you get local index. So what is local index? It's plus and minus 1. You have tangent map of your tangent map at fixed point, because it's kind of transversal, it doesn't have eigenvalue 1. So 1 minus the tangent map is invertible matrix. It has determinant, which is non-zero. Take sign of this determinant, this index map. Yeah, so this, what is widespread definition? Yeah, for example, if F is contract to the point, then tangent map will be 0, get positive sign. Yeah. For contracted maps, you always get sign plus 1.
It's not really easy.
Yeah, for each point it's plus and minus 1. No, but you can have many points with the symmetry. And now what we do? Yeah, it's kind of it's Reidemeister who reformulated things like 10 years after, but it's essentially the same story. You have finitely many fixed points. For each point, you get plus minus 1, and also this twisted conjugacy class. And it's a formal combination of plus and minus is not twisted conjugacy class. You get some of these integer coefficients, and these integer coefficients are this what Nielsen associate to each conjugacy class, certain weighted multiplicity. And the fact it's invariant under homotopy. This is absolutely obvious because if you start to, for generic map, you got isolated kind of transversal 6. And if you move, what can happen, just two orbits, two fixed points collide to each other with opposite sign and disappear or appear. So it's kind of clear that you got preservation of the story. Yeah, so yeah, and then the theory of Nielsen, it was maybe even 26, that the number, so really 100 years ago, that the number of fixed points is bounded below by number of twisted conjugacy classes for which this coefficient is not zero. They should be present. And it's called Nielsen number. It's non-negative number associated to the map. And it was and this subject was central notion for many decades. And actually, there was a beautiful theorem proven by Franz Wecken, who was a student of Reidemeister, 41, that in fact, this is optimal bound. You can, if you replace your thing by at least three-dimensional manifold, you can make exactly this number of fixed points for this map. Yeah, yeah. So it's split self map. Yeah, yeah. So it's absolutely remarkable thing I found. It's kind of like very elementary topology. You get this question, something like similar to kind of like minimal number of cover, like Lusternik-Schneermann category, which is hard to calculate. But here it's really easy to calculate and easy to prove, and we don't use any high homotopy theory. We just use integer numbers, no spectra. And the proof is very, very simple. You choose the at least three-dimensional representative of your homotopy type. It's actually this time this idea of Whitehead about simple homotopy type, but here it's really about homotopy type, simple homotopy type, and you get this representative of them, and get this finitely many fixed points with multiplicities plus or minus one each of them. And if you have two guys have the same twisted conjugacy class, then one can connect by generic path and then make a little surgeries here. Yeah, so you'll do a lot of disjoint one-dimensional graphs from which you make a surgery. Then you can cancel pluses and minuses. Still, you get maybe several pluses. You can again combine them together, get a kind of non-Morse singularity, and make things together. Yeah, and particularly correlate what happens is there's no fundamental group. It's trivial. And then the fact, the calculation is the following: you have induced map on commutative with rational coefficients. With rational coefficients, and it's the only coefficients which I can use. I cannot use integers because we're not free group. I cannot use fields of positive characteristic. I take alternating sum of traces. It will be integer number, and this number could be zero or non-zero. And then if it's zero, you can have a representative without fixed points. And if it's non-zero, you should have at least one fixed point. You can make exactly one fixed point. Okay. Yeah, actually, this original questions, it's not what we like these days. It's minimize some number for Gen 6. We should really keep track of this nice multiplicities. Yeah, so we got, and also, if we have a map, we can iterate it. So it was all this whole thing was designed for study some dynamics to see that that like iterations have many fixed points, and Nielsen himself was interested in maps from surfaces to itself and get exponential growth usually for these numbers. Yeah, so so this Reidemeister trace, as I explained, told you can understand not as linear combination of phi and twisted conjugacy classes because this notion depends on n. But linear combination of conjugacy classes fundamental group over map and torus. So they put on the same kind of like box. It sits together, and as I explained, with ChatGPT we have a little bit more general results, so it's not hard to do to get injectivity in this thing as well. Yeah. So what we get for each positive integer, we get an element, integer linear combination of conjugacy classes of certain group. And as I explained to you, this is zero Hochschild homology of the group ring with integer coefficients. Nothing tricky. Yeah, so we got you get group. This is like fundamental group, and get this H0, and then we can make genetic series. Each term will be finite linear combination, and all things will be infinite. In fact, this variable t, which I added to the series, it's completely dummy variable because for this conjugate class you get rotation number, so it's counted rotation number. So you can say that it's infinite sum, but in sort of completion of this HH0. The question: how one can calculate this infinite series? What you do, it's all homotopy invariant, so you can choose convenient representative. And let's take, for example, choose some simplicial decomposition, find a simplicial decomposition of my guy. And, and now I think that I can approximate my map by piecewise linear map. So I make some subdivision, get smaller simplices, and smaller simplices map to larger simplices. So I get this map. And then one can do the following. Suppose I have some reference point. And for each cell, I choose a homotopy type of path to the reference point. Then what will happen? You get simplex here connected to reference point, simplex here connected to reference point, one maps to another. You get a loop with based loop, and so you get many based loops. How many simplices in subdivision? But this form, we still want to remember big simplex from which we start and big simplex where we start. And what we get a bunch of square matrices with coefficients in the group ring of the fundamental group. What are sizes of matrices? Sizes of matrices is number of matrices labeled by the dimension of simplex from 0 to dimension of your cell complex. And size of the matrix is number, actually, the index set of matrices is I-dimensional simplexes in original decomposition. But matrix element will be again some linear combination of group elements, and number of group elements will be number of things in subdivision. Now, so you get this map, and roughly with the fact that race in cohomology is alternating sum of traces cohomology is the same as alternating sum of traces in complex, you get the formula. This Reidemeister trace of nth iteration of your map can calculate the following. You take alternating sum from type of 0 to dimension, and what you do, you take trace of nth power of this matrix. What does it mean? It's matrix with coefficients in non-commutative ring. When you get matrix with coefficients in non-commutative ring, you take sum of its diagonal terms, but it's not an invariant notion. You consider its modular commutants. It's well defined, it's kind of really basis independent sense. And this is kind of really baby version of Maritin invariance and Hochschild homology. You can see the quotient of matrices with coefficients in ring modular commutant. It's isomorphic to ring modular commutant. It's, where is 6, and then you consider T is kind of like central commuting variables with everything. You can write it sum of finite 6. You get kind of like non-commutative rational functions. And we'll roll such functions. I think it's something called Almgren function series. Yeah, so some developed in this story. Yeah, and this matrices are a finite linear combination of group entries of matrices are finite linear combination of group, or actually not conjugacy classes, of group elements of degree +1. Sorry, it's a mistake. It's group elements. Yeah, it's also tempting to consider something else. Like zeta functions, maybe want to consider these guys and take exponent, but you cannot really evaluate it in something universal. Maybe you can do it some representation. Yeah, so it's because when you want to take traces and then take exponent, and it doesn't really make total sense for me. So I will not do it. I will just do generic series. Yeah. So what goes on? So this Reidemeister traces of iterations of my map are more and more complicated integer linear combinations of conjugacy classes in the fundamental group of mapping torus, and size of the things grows exponentially. And the whole story, it's kind of like infinite information. You get like first maybe 1s and 2s and 4s and 8 classes, something like this. A lot more and more a larger collection of conjugacy classes, and this whole thing it's rational because you can describe in terms of like finitely many matrices with finitely many combinations, and the whole thing is governed by some supermatrix with coefficients in this group ring. Because with the deterministic sum, we can just take all even contribution from even dimensional cells to plus part and odd dimensional cells to odd part. Yeah, what kind of rationality we can see on the nose for this conjugacy classes? It's the notion of rational series in a HH0 for any such group. Rationality can be observed in the following way. Consider any finite dimensional representation of my group to matrices over any field. Could be positive characteristic field now, or the same is homomorphism to a group of matrices of algebra of matrices of some any field. And then we can apply trace in this representation. And what we get? So before conjugacy classes of elements of abstract group, now we have conjugacy class of some matrices. So we get traces of these matrices. You get some series, and this series will be rational. And how to calculate it? We just follow the definition. We have matrix consisting of elements of group ring. I replace elements of the group by matrices in your thing. You get block matrix. So size will be a dimension of representation times the size of this matrix in group ring. You get matrix still of finite size, and then calculate generic series of traces of positive and maybe minus negative part. Okay. Now, so this things which is kind of easily observable part of rationality. You can check it like numerically. If you get sequence like I don't know, first 100 elements of the group ring, 100 maybe twice because it grows exponentially, or 20. Yeah, you can check on computers that, but the approximations is the rational function. pretty useful. Now I go to another subject, which also has history, like during wartime, wave conjectures. So we have now algebraic variety over finite field, FQ. And we choose a base point. Base point will be related for fundamental group. So, yeah, so if you get variety of finite field, then you can change scalars and get variety of algebraic closed field, something like complex manifold. Go to FQ bar. And this variety of algebraic closed field mapped to itself by what's called geometric Frobenius, like all coordinates are raised to power q. So you get a variety of algebraic closed field which maps to itself, and you look what are fixed points. Fixed points will be isolated, will be exactly points of my variety of field FQ, or consider n iterations will be points of variety of FQn. That's kind of like basic insight of like André Weil got idea about homology series and so on, counting number of points. Yeah, and if you count how many fixed points, you get something which look like super trace of some nth power of some matrix. He made he didn't have computers at the time. He made by hand experiments with Fermat curves and stuff like this, and some maybe Gauss sums and some exponential sums. And he observed that you get a nice rationality for geometric series, and Grothendieck was very much impressed and invented modern algebraic geometry for it. Yeah, so that very conjecture. So the geometric series is rational. And now we've got super traces of not canonically determined supermatrix with integer coefficients. Nobody really wrote or speak about matrices. It will be characteristic polynomials of matrices, but they have integer coefficients at the end of the day. And my goal is to propose generalization of Weil conjecture using Reidemeister traces. It's actually really on the nose. You don't know why people miss it. Maybe the subject is Nielsen, this Nielsen-Reidemeister series was really in a very, very bad shape. It was like backwater of topology. Yeah. So some people maybe in surgery theory, like students of Andrew Ranitsky, interested in, but it's really, really backwater. Yeah. Yeah, and the picture is the following. We understand that if you get variety of finite field, this has notion of covering. You get profinite group, the fundamental group. When you get base point, and this fundamental group is semi-direct product of Z hat, which is Galois group of a finite field FQ bar, which has canonical geometry of Frobenius. It's like the circle for which you drew this metric cylinder. And this group acts by automorphism of the geometric fundamental group. When you change scales to FQ bar. And then what people really have always in mind that you get like mapping torus when thinking about topology, what are varieties of finite field. You get little circle represent with geometric Frobenius, and you get fibers like self-map for some surface. And this thing it's not really usual topology, because for this map, if X is a curve, compact curve, then the map on the fundamental class of the surface, remaining surface, will be not identity, but will multiplication by Q. So it's like not invertible map, it's some kind of self-covering. Yeah, so it's the usual thing, and now it's actually completely clear. For each point of variety of QL, you get it's not my base point; it's somewhere else. You get local Frobenius. You get conjugacy class of this group. Yeah, so nothing mysterious and of degree n, because it's not of degree n. And it looks at analog of multiple multiplicity is +1 for any fixed points. It's what happens in wave conjecture, we realize that number of points of FQ power m, it's a Lefschetz number of some map, and each point contributes to multiplicity +1. Why it's +1? +1 because first of all, we can try to think it's something like complex manifold, algebraic closed field, something like complex manifold. We get intersection, transformation number, we get multiplicity +1. But also it's +1 by another reason, because you can imagine that I get some periodic thickening, like in Bloch approach to rationality of zeta functions. And in this periodic thickening, this map raised to power p, it has derivative equal to 0 mod p. So it's contracting map. So by any reasons, its multiplicity is +1. And then, of course, we can define Reidemeister traces for iterations, excluding 0 iterations. And the Reidemeister trace for 0 iterations, one can get idea from topology, what it will be till some integer. And for nth iterations in geometric series, so what it will be? It will be somehow all integers now starting from 1 to infinity. It has this dummy variable t, which will count degree of extension, and then it takes some of our conjugacy classes of this Frobenius associated to points of FQN. And one can make super optimistic conjecture that this series is rational. It's actually something really fantastic. It's a claim that it's very tricky for finite groups. I claim that there's 2 finite matrices. Each matrix is finite linear combination of some elements of this profinite group. And that is, you take this Rayleigh matrix cross and you get finite linear combination, and then you get exactly this Frobenius.
Your generalization.
It's my generalization of a conjecture,
There is no exponent, and you did not consider really narrow, because it's already exponent irrational.
No, it's the same. So the sum of traces, this is just a formulation. It's nothing. It's not only rational, but given by traces of n-spiral matrices.
So how many examples do you know?
A little bit. No, the story. The first thing, it's kind of like impossible to check, because we have these profinite groups. Maybe it's too optimistic. But one can formulate a more modest conjecture, which is also stunning. You use any finite dimensional representation of this group. And if it's a rational element in the 6, then you get a rational element in group ring of this to where you map, and then it will be kind of a more controllable object. And algebraic geometry produces plenty of such representations. It's called motivic sheaves, or elladic representation of the thing. You get elladic representation with break varieties compressed by X. One considers just family of varieties and smooth projective family and take homology of fibers. But in general, when you get this family of varieties, they have something analog of Mumford-Tate group. It will be some reductive group. And you can imagine to get some reductive algebraic group over elladic numbers. So it is some other prime number. And you get representation to group of points of this reductive group. And then we get elements, sequence of elements and zero Hochschild homology of this guy. It will be exponentially growing collection of conjugacy class, like in topology. And this rationality in this huge group, which is inaccessible, implies rationality in kind of groups which we understand better. GFPL, it's will be some compact, locally compact groups. yeah, first there is some first kind of sanity check. If you consider, for this group, consider finite dimensional representation to JLN for some n. So, as I explained, this representation to group of JL it's a sanity check when we get rationality here. And here, so it means that we get a local system, not coefficient of the group, but some elliptic shift. And so we get a representation group to group of matrices, dimension equals to representation, and then we should take sum of traces. And that's what people usually do with shifts. You get some shift, you calculate some points as trace, you get a bunch of numbers. Then I take some of these guys, it will be trace in R gamma. Yeah, maybe you should consider commutative with compact support with coefficients in local system. So it means that you get automatically rationality. Which, yeah, so for individual representation of this reductive group to group of matrices, rationality is what algebraic geometry is good for. Yeah, so it was a very good sign that 6 matches. Yeah. What is absolutely not trivial and has really no reasons that this simultaneous rationality for one representation will be also for other representation. Another representation is always governed by some finitely many matrices. And a couple of months ago, with Ilya Gayura, my postdoc at IHES, started to make some numerical experiments, and the simple things to calculate was some basic function. So, what is variety? Variety is affine line minus 0, what's called JM. And I defined two-dimensional representation in elliptic representation. Actually, there's actually no role here. It's just a decoration. It is the following. I assume that any such that I have a primitive root of order p in my 2K. That means that some sort L equal to 1 mod p. And then I want to have analog of Bessel integral. What is Bessel integral? It's Fourier transform. It's Fourier transform of function exponent of 1 over z. And instead of integral rate sum, it's called Klosterman sum. Again, very, very classical object, very much studied in the subject. And as an exponent, you take the following thing. What I'm doing here? I say that I have I want to associate like two-dimensional representation of the fundamental group, or for each point of my variety of some extension of finite field, I should get 2 by 2 matrix. The 2 by 2 matrix is determined essentially by tracing determinant. Yeah, there is some delicate point when matrix could be not semi-simple. In actually all these conjectures, I have to go to semi-simplification of matrices. So that things it's impossible to detect on semi-simple part. Yeah, so if you have matrix 2 by 2 matrix is determined by trace and determinant. And I said this conjugacy class is the following. It's determinant should be p to power n. Sorry, it's a mistake. Determinant should be p to power n of the matrix, and trace is this value of basic function. Oh, sorry, it's a mistake. It should be minus because it's one-dimensional integral. It's odd number should be. Yeah, sorry for some mistake. It's minus the sum. Trace should be minus the sum. It's minus the sum of what? You consider elements non-equal to 0 because they want to put 1 over z somewhere. And here it's an analog of exponent. I get element on a finite field. I want to get some number, take exponent to it. What to do? I take a trace in the fields, the field extension to Fp, get residue mod P, consider P's throat of 1, let's say in complex numbers. I don't really want to go to direct numbers, and get the 6. Yeah, oh, so I wrote it, Z, it's actually Z, it's belongs to cyclotomic field. Sorry, several misprints this formula. You get the element in cyclotomic field order P, and get just for each thing. Yeah, and these things come from a representation to J2 of fundamental group. Fundamental group of fine line in positive critique, it's enormous because you have some kind of like wild behavior at infinity. It's analog of irregular singularity, so it's very different from Naive. So it's rank 2 local system, and what one can do, one can make many new local systems taking symmetric power. Yeah, determinant is kind of trivial story, but for SLN you got interesting representation, symmetric power of two-dimensional representation. Yeah, so for each M we can make M symmetric power, but this from rank M. And now consider cohomology with coefficients on this same M. What is it? It's actually space of dimension, if I remember, something like M minus 2. And what is it? You consider certain very interesting Calabi-Yau variety of dimension M, namely in homogeneous coordinates you write sum over M guys is equal to 0, sum of inverses is equal to 0. It's absolutely remarkable variety, which I can give a whole lecture about this variety. It's actually classified regular, it's model space of M bonds with size equal 1 on plane, because you can imagine to have like complex numbers with absolute value equal to 1, then to kill some complex conjugates equal to 1. So it's really a regular one, and it has great birational automorphism group. But some part of automorphism group is very stupid, just the permutation of coordinates. And now consider in primitive cohomology, the part of cohomology when this permutation group is by side. And it has Hodge numbers 1, 1, 1, 1, 1. It's kind of a growing family of varieties, and I think QFT people, it's kind of like most basic integrals which people consider like in Feynman diagrams. It's called something like sunset graph. Yeah, some picture like this. Yeah, that's things related to basic functions. Some remarkable family of more and more complicated Calabi-Yau varieties. And what is the claim? That if you fix prime number and want to understand like eigenvalues of Frobenius in this more complicated things, this is always covered by some finitely many matrices coefficients in group, some finite collection, some finite data which you can send by email. Not really. Maybe, yeah, maybe I can show. If I'll have more time, I'll be able to produce actual matrices coefficients. And we check numerically, and then for p equals 3, I think I have now essentially explicit formula, which I'm not ready to show, but it's something like sum of 7 matrices with size 3 by 3, which have again coefficients of some matrices size 2 by 2. Yes, some kind of bit complicated thinking, but it's finite expression. There is something a little bit unfortunate in this example. At least what I see at the moment when I try to write kind of following recipes, what I'll get, I get matrices with coefficients in a group ring with not in Z, but having some denominator, 1/6 in this example. And where it comes from, and actually it's kind of provable fact. It's kind of like a coincidence that this two-dimensional representation, if you have like a field of 3 elements, actually wait 3. First we try 2. And for 2, it turns out that the representation is finite image. It's a finite group. So it's not really interesting. For finite group, one can really figure out without going to deep algebraic geometry. For 3, you get something more interesting. And again, some little coincidence, you get not circular atomic field, but actual integer numbers. One can call this trace of Frobenius field integer numbers. And what is going on? And in fact, the whole thing happened to coincide to first homology of universal elliptic curve over modular curve, this kind of level structure gamma 1, 3. It's called congruent subgroup. And traces of powers of Frobenius are the same traces of powers of what's called Atkin operator, acting on modular forms of various weights. So this minus zero modular symbols. So if you want to do calculation for modular form of certain weight, you go to, it's correspond to symmetric power with this representation symmetric group. And what is going on? You get this congruent subgroup gamma 1, 3. In fact, you should make it's already has some little torsions, retortion, but unfortunately, should have add also two torsion, and it's unavoidable. There are something like plus minus the subsequent Atkin involution on there's a plus minus part in modular forms, and the fact that gamma 1, 3 should make double extension, which has naturally two torsion, because you add some matrices with determinant minus 1. Not 1. Yes, it's a bit long story. It's called gamma 1, 3 star. So you get group with non-trivial torsions. It's virtually after torsion. It's classifying. It's actually free product of some Z-mod 2, Z-mod 3, something like this, and it's classifying spaces an orbifold. It's virtual fundamental class, but because orbifold, when consider resolution of some like trivial representation, you get some projectors and you get some denominators in the formula, little denominators, which I don't know how to at the moment how to kill them. And so you get these unfortunate denominators, and what you calculate the traces of sorry, it's Hake operator. You calculate some trace of some element of this group ring in direct sense in some finite dimensional module, and for this module you make projective resolution, and this is something called Dennis trace. One can speak about categorical traces, but this is really elementary mathematics at the end of the day. So this, the moment I start this little problem with denominators, but it's even without this problem, it's already remarkable. Why I think it's solvable because at the end we get the linear combination of conjugacy classes. So in the intermediate calculation, we get little denominators. This somehow cancelled. Maybe some good representative will have no denominators. Rationality, yeah. Yeah, it maybe will be like 1/2 of the trace of get rationality. What is potential application of all this thing? Kind of. It was quite driven. I think Frobenius is and the map of some space. In some situation, one can really, like in photoric variety, one can do actual Frobenius, like a projective space. You raise coordinates to piece power, and you see identification of fixed points over complex numbers and fixed points over finite field, but not terribly canonical, but this numerology works well. What I claim that one eventually gets something absolutely remarkable. One can get canonical identifications, many canonical identifications, depending on how lucky you are, between varieties of finite field and real dynamical systems. Kind of like C-infinity manifolds. So this. Yeah, suppose I have this at least one trivial example. The things works more or less, and what I have, like, for example, in this example, I have values of these Bessel functions. Values of Bessel functions are between -2 square root of q to 2 plus square root of q, and get q such numbers. So many of them coincide. But if the motif is more complicated, or group has rank bigger than one, bigger than the dimension, then you get this traces of Frobenius, so symmetric powers Frobenius will be much larger integer numbers. There will be so many such numbers that kind of there's very little chance that they coincide unless you sit on the orbit of Frobenius, because you get more possible characteristic polynomials than numbers of the points in the field. And then what is possible, it's kind of nothing contradicts to the following possibility. Suppose we, in such situation, we have these conjugacy classes are distinguish all elements or all extensions of a finite field, which is pretty likely. Then and suppose we found this encoding some finite combination of some matrices. Let's say this integer coefficients and of a group ring of finitely many linear combinations, some matrices, and this matrices generate some finitely generated group. Maybe it's fundamental group of something, and then we have self-map for some completely unrelated space which has the same numerology, and assume that for this actual dynamical system, all fixed points have multiplicity 1. Yeah, we know there is at least one mechanism which guarantees it. It's meant to be contracting map. It should be not invertible map. It doesn't need to be invertible. So we should have contracting map, which or design some kind of like mixed behaviors. Yes, so the things. So it means that you get fixed points. These orbits of your periodic orbits you can distinguish by conjugacy classes in this representation. Fundamental group should have representation to some matrices of some big size of integers or rational numbers, and then if conjugacy class are all kind of likely different, then you get canonical one-to-one correspondence between periodic orbits and points of a variety of finite field. Now that so you get this numerical coincidences between some counting in geometry and natural geometry and dynamical system gives you canonical identification of orbits, which really very exciting, because like for finite field, this big open problem, we do not know any systematic construction, how to make extensions of arbitrary degree finite fields. We know they exist, but none of them is better than another. And there's no kind of referred irreducible polynomial of large degree over F2, for example, F3. And what I can imagine that you'll have some dynamical system which happily coincide, let's say, with some local system on A1, or maybe 1 minus 0. So orbits will be reducible polynomials. And now we should look on periodic orbits of very, very high degree, and it will be fractal set. And in dynamical system, people have control. Maybe in some points you get really can pinpoint points exactly of period n for each n. And then it will be canonical after making all this machine. You get canonical irreducible polynomial, yeah, so it's in there. And if you choose different models with different contour correspondence, different position, or canonical. Okay, thank you.